Hey guys, so today I would like to show you some examples of energy. We will be applying the equations that we have learned for conservation of energy, gravitational potential energy, kinetic energy, and efficiency. So observe this problem here. There is a skater up a quarter pipe with the initial velocity of u. I'm assuming that the magnitude of that velocity is 1 and the directions to the right. Now something happens here, probably he does some ollie or he just goes here down the ramp. Anyway, there is some transfer of energy. So he goes down a height of h to a new position now, and now he has some different velocity v. If there's no loss of energy here, what would be his final velocity? Now the first point to consider is, why do we have to assume that there is no loss of energy? How would energy be lost in such a case? Well, can you simply imagine if a skateboarder was jumping through this gap here? What would happen when he lands? Would we hear it? Would there be any heat? So usually we wouldn't hear it. So there is some sound energy. And where's that sound coming from? Well, from the energy that you're using here, right? So some of the energy on that jump will be released as sound. Also, there is some friction with the wheels, there is the impact on the floor, so those will generate heat, which is another type of energy. So we're assuming that there's no loss, so there's no sound, no heat. Obviously, that's an approximation, but that's fairly good for what we're trying to do now. So we need to apply our conservation of energy. So what does that mean? Well, the energy before has to be equal to the energy after. So I'm going to label this point 1 and I label this point 2. So the energy at point 1 has to be equal to the energy at point 2. So what is the energy at point 1? Well, what kinds of energies will I have here? So since this skateboarder is moving, there will be some kinetic energy. Also, since he's higher than in the second time here, there will be also some gravitational potential energy. And those should be equal to our kinetic energy here at the end. Now, you may argue that there is some gravitational potential energy because, as I told you last lesson, when you're on Earth, the energy is actually, the force of gravity is actually pulling you towards the center of the Earth. But the point is, if you compare 2 points, one here and another one, which let's say you're in Everest and the other one you're at sea level, the change of energy will only have to do with the change of height. So we don't have to consider all of this, because if we consider it here, this radius of the Earth, when we subtract by this one, then those two will cancel out. So as potential energies, what really matters is the difference in the energy. Well, so kinetic energy at the beginning would be mu squared over 2 plus gravitational potential energy at the beginning, mgh, should be equal to the kinetic energy at the end, which is mv squared over 2. So we can cross some things out here, mass, mass, and mass. So it seems that the speed here doesn't level with the mass. It doesn't matter what's the mass. If this mass was 50 or if this mass was something else, our velocity would be the same. That's really interesting. Well, now let's rearrange that equation. So we can multiply everything by 2 here, so we can get rid of those 2's, and this term will be multiplied by 2. So since we want to find this final velocity, I'll leave it alone. So that's my subject. And what I'll have is a square root, because it's velocity squared, of u squared plus 2g8. This is similar to something that we have seen before. When the initial velocity was 0, we just had roots of 2g8. But now, since the starting velocity is not 0, this will not be equal to simply that. There will be another term inside of the root here. So if we put our values in, u is the initial velocity, which is 1. So 1 squared is 1. Plus 2 times gravity. Gravity is 9.8 times the height, which was not given. So I'm going to tell you, I forgot to write this down, 2 meters. Okay, so this will be times 2. V is equal to, and then if we multiply all of those, we should calculate this root to be approximately 6.3 meters per second. Now, a few things to observe. First one is that the velocity, if you do this practical, if you go with your friends after the quarantine, obviously, if you go to your friends to a quarter pipe and you do some practicals, you test this, you will most likely find some velocity which is lower than that. And that is because here, again, we have assumed that there's no loss of energy. But if there are losses of energy, so if there is heat, right? If you, for example, if you walk a little bit in your skateboard and then you stop and touch the wheels, you will probably feel that the wheels are a bit warm. That's because of friction. So there is heat, there is some energy being lost due to heat. Also, as I told you, there's sound. When you jump and you fall, right, you make an ollie, and then when you fall to the ground, there will be some sound. And that sound has to come from somewhere, and that means there is some loss of energy. And that sound is also energy traveling. So in practice, this value would be lower, would be less. But when you're told to neglect any losses of energy, that would be a result. So what if I told you that his measured velocity was actually 5 meters per second? So you could be asked, how much energy was dissipated? For example, sound or heat, right? So how much was dissipated? So we may calculate this difference now. So what was the energy associated with the skateboarder at the end? So kinetic energy is mv squared over 2. So the measured one, the speed was 5, right? Not the theoretical one, the measured. I told you that. So the mass was 50, our speed is 5. So if we do that, that's going to be 625 joules. So this is with losses. This is considering the losses. Now, what about the theoretical? So in theory, we did calculate this speed to be 6.3. So if no energy was lost, that would be our speed. And if we measure this energy, it would be around 992 joules. I'm keeping 3 significant figures here just because. Now, this is assuming no losses. So, if I ask you, what's the efficiency of this process, right? With this difference, you find what were the losses. So if you subtract 625 from 992, you will find this difference to be 367 joules. about a third, it seems, or a bit more of the total. So what is the efficiency then? So it's useful energy or power divided by total energy or power. In this case, since everything here is energy, let's just work with energy. If we had powers here, we would work with powers. So the useful energy here is the one with losses. And the total energy is the one without the losses. So take a look. This will give us a number which is between 1 and 0, and the highest, so 1 would be 100% efficient. It never happens, all right, in reality, but an efficiency of 1 or an efficiency of 100% would mean that all energy put into the system is useful, but that never happens. So if you do have an efficiency of 80%, let's say, that means that 8 over 10 or 4 over 5, right? So 80% of the energy that you put into the system is useful, 20% is wasted. So if we go forward with this, what would we get? About 63%, right? If you calculate, you're gonna get 0.63004 something. And then if you round to 2 or 3 significant figures, that's 63%. So another fairly simple but also very useful example is a pendulum. So assume that this is a pendulum. Usually we assume that this angle is fairly small. I'm just making it larger so you can visualize in a better way. So if I let this pendulum go, it's going to swing back and forth. And if we were to analyze the energy transformations which happen here, what would they be? So let's call this point 1 and let's call this point 2. What kind of energy do I have at point 1 and what kind of energy do I have at point 2? Alright, so at point 1 we do have some gravitational potential energy when compared to the second point here. Just like before, what's gonna matter is just a change in height. I could get all the height, right, the whole distance all the way to the center of the Earth from point 1 and from point 2, but when I make this difference, then what will matter is just the difference between them. So let's just make our lives easier. So gravitational potential energy. Since at the beginning this motion is not happening, right? It's stopped, so it's not moving. It's in the imminence of moving, so the acceleration gravity here is going to make it move. So kinetic energy is 0. So gravitational potential energy is larger than 0, kinetic energy is 0. In the second point, there will be a lot of speed here. So this velocity will not be 0. So kinetic energy is larger than 0, but gravitational potential energy will be equal to 0. Again, we're talking about the difference here. So there will be gravitational potential energy here. If I cut this rope, this will fall down because there is gravitational potential energy. However, if we are just comparing those 2 points, this is 0 compared to that one. Well, let's apply our conservation of energy here. So since we only have gravitational potential energy before and kinetic energy after, we may just say that the gravitational potential energy before is equal to the kinetic energy after, right? This is point 1, this is point 2. So what is the gravitational potential energy before? mgh. What is the kinetic energy after? mv squared over 2. Now again, the mass does not seem to matter. So if we are asked what is the speed of this particle when it's going through the bottom here, we could easily calculate. We can just work v squared is 2gh, then v is the square root of 2gh. So just so you have some idea of how large it's going to be, if your height is, let's say, 1 centimeter, which is 0.01 meter, your speed here would be root of 2 times acceleration of gravity times 0.01. And if you work this out, you will find something around 0.44 meters per second, which seems a bit large for such a tiny distance, but that's it. Now, let's take a look at another example now. This one, we will basically focus on efficiency. So let's say that there's a motor, and this motor is being used to lift some weight. Okay, so somehow it's turning here and there's some weight being lifted. Now, let's say that the force here, gravity, on this weight is 150 newtons. So that is the force that motor is actually overcoming. The height that this weight has been lifted was a total of 7.2 meters. The energy supplied to the motor, so that's our E total, that's the energy which is supplied. Some of it will be lost, between quotes. It's going to dissipate into the atmosphere, but the total energy which is provided is 3.5 kilojoules. First question, what is the change in energy? Second question, what is the efficiency? So let's take a look at those two. The change in energy here is simply the change in gravitational potential energy. So this will be mg delta h if it's change in height, or simply h if we are considering, for example, this to be 0 and then it's 7.2 up. So our mass here, well, mass times gravity, that's weight, which we're given as 150. So this would be 150 newtons times 7.2 meters. And that should be 1,080 joules. So a bit more than 1 kilojoule. Now, to calculate our efficiency, we have to divide the change of energy, in this case the change in gravitational potential energy, by the total energy which was supplied. So in this case, our gravitational potential energy change was 1,080 joules, and the energy which was supplied by the motor was 3,500 joules. So this would turn out to be around 31%.